Welcome back. It has been such a long time. And let me first discuss what we're doing here. I know I have videos for AP Calculus AB based on units and lessons, chapter 2, day 1, chapter 2, day 3. But I have done something a little different. Here, let me open that up so I can see my time. I have kind of thrown out the pre-calculus curriculum, and I have started to teach pre-calculus as it is a general calculus AB course, meaning pre-calculus now learns almost everything calculus does, calc AB. We can kind of go as slow or as fast as we want. They don't have to take the final, okay, the AP exam, in May. And I do this for two reasons. One, pre-calculus kind of felt like an algebra 3, and it didn't feel like it brought enough into calculus or prepared kids enough for calculus. So when kids were getting into calculus, they were kind of getting steamrolled. So what I did is my calculus curriculum has now moved down to pre-calculus. Okay, it is general. We don't take the AP final, and we can spend as much time on material we need to if kids are confused. So that leads me to this. What do I do in my AP calculus class if pre-calc is learning calculus? Well, what I do now is I have kind of changed my AP Calculus AB to more of an AP Calculus AB review. So we go over the important information from each of the units, starting with Unit 2, Unit 3, Unit 4, Unit 5, Unit 6, and Unit 7. Okay, and their limits and continuity is Unit 2. Unit 3 is derivatives. Unit 4, I believe, might be like applications of derivatives, something of that nature. Then we go to integrals, differential equations, things of that nature. And we end up with Unit 7, which is area between the curves and volumes. Okay? So I'm going to start going over the review for each one of these units in these videos. Now, I also have packets on my website, all right, that as soon as we finish the review notes, which might take a couple of days, 3-4 days maybe, to do these review notes, I just give them problems after problems. So for example, we are going to start the Unit 2 Limits and Continuity review notes, okay? After that's done, I have hundreds of problems. It feels like hundreds of problems. It might only be 100, but we're just going to do problem after problem that are deal with limits and continuity. Then we're going to go to Unit 3 and go over the review notes for that unit, not just like 3-day 1, 3-day 2, but a review of the important stuff of that whole unit. And then problems after problem after problem. All right, and this is the first year I'm doing it like that. This is the second time they've seen this going around. So hopefully they're a little bit more familiar with it, and we are doing a massive amount of problems. Where before we learn a unit, we do some homework, maybe you have some problems to practice here and there, then go on to the next topic. Learn it, do some homework a little bit. This AP Calculus AB course that I'm teaching, this review one, focuses more so on doing the work than learning it because we've already seen it before. And I'm hoping that will give us better scores. And, we'll see. This is our first year. So now I've wasted almost 4 minutes explaining to you what this is all about. I will not do this for Unit 3 notes, Unit 4 notes, etc. Let's get started, shall we? Boom. Okay. Average speed. First of all, it's a ratio, okay? In calculus, we call it f of t plus h minus f of t all over h, okay? Where h is really a change in time, and these function notation up here really represent the y value, okay, which might mean distance or whatever in calculus. So really, change in y over change in t, it's something we've seen before, okay? It's a change in the function, which is your y value, over a change in time. But you may remember this as change in y over change in x, which is like y2 minus y1 over x2 minus x1, okay? So average speed, you'll be given two positions, All right, it's really just a change in y over change in x. Okay, it's a slope between 2 points. We've been doing that since math 8 maybe. After average speed came instantaneous speed. Okay, and instantaneous speed is that same expression, that same rational expression. I'm trying to sound smart. It's really that same fraction. Okay, f of t plus h minus f of t all over h. But now it becomes a limit. Okay, yep, that was my green marker. My limit as h goes to 0. All right, now there's a problem. H is alone on the bottom. It is the denominator. We cannot have a 0 on the bottom of a fraction. We cannot have a 0 as our denominator because values become undefined. So if you can recall, we need to algebraically manipulate this after we plug in all of our values and try and get rid of that h on the bottom. And the result will let us know what our instantaneous speed is. Now, don't worry, we'll have time to practice this later. This is just a refresher of the material that we're going to be using on all these problems that we're going to be doing, okay? Definition of a limit. Yes, that is my Twitter handle, at Visca the Teacher. I have a YouTube channel. As you know, you're watching this video right now. youtube.com/Visca the Teacher. Okay, which is where all my videos are, but that is my Twitter handle as well. Okay, so the definition of a limit, okay, the definition of a limit is as follows. Okay, the limit of my function, okay, f of x, as x approaches some value c, will equal L. Now, this can be any expression. Let's say it's x squared plus 3. Okay, the limits as x approaches 2, okay, would equal some number. This would always be a number, okay? So if we did that right, we should end up with 7. Don't worry, we'll have more practice. But I know sometimes people see all these letters everywhere, okay? It's no big deal. It's when we actually do these things that it makes more sense, practicing them. So this is some function we're given. It's going to equal some number, and most of the time, that's also a number. I mean, every once in a while, they give you a letter, like on a multiple choice question, but it's so simple. You plug in a letter for x just like you would plug in the number 2 for x, okay? So let's find the limits of the following. Let's see if we can blow this up a little bit more. There we go. Love it. So for this first one here, find the limits. Okay, it's the limit as x approaches 2. So all I'm going to do is I'm going to throw a 2 in for all these values of x. And I like to put parentheses whenever I'm inputting a value. So this would have been x squared, but instead a 2 is going in for that x. Plus 2 times x, but a 2 is going in there, plus 4 all over x plus 2. So x plus 2. And 2 is going, that's a lot of 2's, wow. So let's simplify this. This is 4 plus this is 4. You can't forget that, plus 4 all over. Wow, we had a lot of 2's. Now we have a lot of 4's. Okay, 4 plus 4 plus 4 is 12 over 4. And if I divide that, my limit is 3. Okay, the limit as x approaches 2 of my function is 3. And what does that mean? Well, simply put, if I had a graph and I graphed this function right here on my axis. Here's my x, here's my y. All right? As x approaches 2, here's the number 2 on the x value. My y value would approach 3. Okay? My y value would approach 3. So, it doesn't matter. I don't know, if I came this way from the right side and came closer to the x value of 2, which is right here, and I came from this way, they would approach 3. Okay? It can be a hole here. It does not have to be a coordinate. It just has to look like what it's approaching from both sides. Looks like it's approaching a y value of 3. Looks like it's approaching a y value of 3. Okay? That's just a quick refresher. All right, let's try another one of these bad boys. Let's try the second one. I've got to throw a 2 in for my t. So this should be as t approaches 2. All right, well, right off the bat, I see a problem. If I throw a 2 in here, 2 squared is 4, and 4 minus 4 is 0. I would end up with a 0 on the bottom. So let's see if I can manipulate this algebraically and get rid of that problem. Well, I know the top can factor. That's t minus 2 and t minus 1. Minus 2 and minus 1 multiply to positive 2, and those same two numbers add to negative 3. Factoring never goes away in math, okay? T squared minus 4, that's a difference of perfect squares. That's t minus 2 times t plus 2. Oh, beautiful. My t minus 2's can cancel. So I end up with t minus 1 over t plus 2. Now I can throw my 2 in, okay? That's 2 for my t minus 1 over 2 in for t plus 2, which is 1/4. There we flippin' go. Now, another quick reminder. Okay, whenever we cancel something out that would have made our function undefined. This would have been undefined at t equals 2, right? That would have made our function undefined. Whenever we cancel that and get rid of it, on our graph, that means there's going to be a hole at t equals 2. All right, let me explain that. Remember how I was saying earlier that the limit is telling me that now this is t instead of x. As t approaches 2, my y value looks like it should approach 1/4. All right? So as I graph my original function here, if I come from the left, it looks like it's going to approach and hit 1/4. As I approach, here's my x value of 2. Okay, it's going to look like it's going to approach a y value of 1/4, right? It looks like it's going to approach right there, that intersection. So yeah, it looks like it's going to approach that way this way, and this way might be like, come down. It looks like it's going to approach that way. However, 2 does not work here. It makes it undefined. Since we crossed it out, there is a hole. It is not an actual coordinate. It is a hole. So again, we don't have to have a point there. The graph just has to look like it's approaching 1/4. As I come this way from the right side, it definitely looks like it's approaching 1/4. As I come from the left side, it looks like it's approaching 1/4. All right? Let's try this last one. Obviously, I cannot throw or substitute a 0 in for this x. So I'm going to have to factor. I can take an x squared out of the top. So we have 5x plus 8 over, and I could definitely take an x squared out of the bottom. That leaves me 3x squared. Move this thing out of the way. Minus 16. Okay, these cancel. Remember, since I cancel something, x equals 0 would have made it undefined, right? But since it's gone by, I canceled it. In my graph, there's going to be a hole there. All right? So now we got this to work with. This is nice. Now we're just working with this. We can definitely throw a 0 in for x here. So it's 5 times x, which is 0, plus 8, over 3 times x squared, which is 0, minus 16. Okay? Anything times 0 goes away. 8 over negative 16, not just 8 over 16, but negative 16. Can't forget our sign. Negative 1/2. Bam. There we go. Okay, so now that we've practiced some limits, let's take a look at one-sided limits versus two-sided limits. All right, the first thing I have listed here, is that a little, oh yeah, it's gonna have, why don't I do this? Okay, why don't I group these together? So then I can increase this in size so it's better to see. Faboo. And then I can take a sip of coffee while I'm walking back. Mm. Oh, it's so good. So good. Now, one-sided limits versus two-sided limits, all right? One-sided limit. What is that? All right, well, that's a limit just from one side, okay? I just spoke about on the previous slide that if I have a graph here, and you don't have to write this down, okay, if I approach the number 2 and the first one it approached 3, as I approach it from the right side and from the left side, okay, as I approach 2 on the x value, it approaches a y value of 3. Okay, it's what it is approaches. It could be a hole there. It doesn't have to actually be the coordinate, but that's fine. But now, when we're talking about, actually, let me undo that. Now, when I have this with a little plus in the upper right-hand corner, that means I don't care about approaching that value from the left side. I only care about approaching C from the right side. Let's say C was 2. I only care about approaching 2 from the right side. I don't care about this left side at all. I just care when it approaches from the right side. All right? And vice versa here. If I have a little minus here, I just care about approaching my value of, let's call this 2 instead of C. I just care about approaching 2 from the left side. So I don't care as I approach it from the right side. Okay? That's what one-sided limits, that's what they are. Okay? So let's get rid of our 2's and everything, and we'll say this is, I guess, finding the y value. Okay, this equals, and it's not really the y value, it's the y value it's approaching. The y value you're approaching as you get closer to, in our case, C, x equals C. Oh, you like what I did there. X equals C from the right. It doesn't care about the left. This little plus up here means from the right. Okay? Now, the minus is the same exact thing. These ditto marks means I want this to say the same exact thing. Okay, y value approaching as you get closer to x equals C from the left. Okay, from the left. All right, that's what that means. Now, when we don't have a plus or minus, okay, right here, it's just x approaches C. That means it's the y value approaching as you get closer to x equals C from both sides. Okay, so you have to consider both sides. All right, for when there's no plus or minus here. This is a two-sided limit right here. These ones are one-sided limits. Now, in order for your limit to exist, okay, in order for a two-sided limit to exist, your limit as x approaches C from the left has to be the same as your limit as x approaches C from the right, okay? So let's say this equals 3 as I approach it from the left, and let's say this equals 5 as I approach it from the right. If this is the case, the limit as x approaches C does not exist, okay? These have to be the same in order for this to have a limit, okay? All right, let's take a look at this step graph. It's the int function, all right? Step graph right here. The limit as x approaches 3 from the right, this little plus thing here, 3 from the right. Here's where x is equal to 3. As I approach it from the right side, it looks like it's approaching right here. A y value of 3, okay? That's what the coordinate looks like it's approaching, okay? A y coordinate of 3, all right? But look what happens when I approach 3 from the left, okay? I'm still approaching my x equals 3, but I'm coming from the left side. So I got to follow the graph, right? Boom, then it jumps up, boom, then it jumps up, boom. As I get closer, it looks like it's approaching this point where y is 2, okay? Now, not from left or right, from both sides, all right? As I approach it from the right, it's 3. As I approach it from the left, it's 2. It does not exist unless those are the same numbers. It has to approach the same value from both sides. All right? There we go, children. And this point looks like a really good place to stop. We'll stop here and we'll continue with part 2 of our Unit 2 Limits and Continuity Unit Review Notes. Okay, so take it easy. Don't stress out. That's the bell. Perfect timing. I will see you for part 2.